Okay, we'll start the second half of the session. To lead us off is Ariel talking about constraining Lambda CDM with Galaxy clustering.
Thanks. First of all, thanks for the organizers. Thanks to the organizers for the invitation. It is a pleasure to be here. This is the first time I'm here as an adult, but I used to live here because my father is a mathematician. He did a postdoc here in Berkeley shortly after I was born. So until I was 2.5, I lived here. Of course, this was a really long time ago. Yes, so today I will talk about constraining cosmological parameters with galaxy clustering measurements. In particular, I want to focus on Lambda CDM. And this is work done with a lot of people that I just want to highlight the my main collaborators on this. So this is an outline of my talk. I will show anisotropic galaxy clustering measurements from BOSS. I will try to highlight what is the information content that they contain. Then I will talk about the modeling of these measurements and how we can use these models to extract cosmological constraints, combining BOSS with Planck and just using BOSS data alone. And then I will finish with some short discussion, if there's time, on the consistency between low redshift measurements and Planck data. So just a summary to say what we were trying to do. So now we live in an era where a variety of cosmological observations have really cemented the Lambda CDM model as our standard model. So what we want to do is to stress test this model. Now, present day CMB measurements are accurate enough to give us good constraints on the basic parameters of the Lambda CDM model. So what we can do is to use those CMB constraints to predict what is the redshift evolution of the expansion history of the universe and the growth rate of cosmic structure. And then we can try to measure these things directly at low redshift and compare our measurements with the predictions as a stress test of the Lambda CDM scenario. And the good thing about galaxy clustering is that it provides us with both of these types of observations. And this is the main driver for the construction of these increasingly larger galaxy redshift surveys. And today, the largest galaxy redshift survey available is BOSS, the Baryons Oscillation Spectroscopic Survey. I don't need to say anything about BOSS. You know everything. I will just say that it contains over 1 million galaxies in a redshift range from 0.1 to 0.7. And yeah, we did already a couple of years ago a lot of analysis of extracting cosmological information of anisotropic galaxy clustering measurements from BOSS, measurements like this one that shows the two-dimensional correlation function as a function of the S perpendicular and S parallel. And it shows, lots of interesting features, and these features contain cosmological information. The main information comes from the BAO peak, this ring-like structure that we see here, and also redshift space distortions that are squashing the contours along the line of sight. So this information essentially gives us distance measurements, so the measurements of the angular diameter distance and the Hubble parameter from the BAO, Yakov-Pachinski distortions of the BAO ring, and the redshift space distortions give us information on the relation between the velocity and the density field, and this can be also expressed as constraints on this quantity F times sigma. And this is why this constraining these quantities has been the main focus of lately of galaxy clustering measurements. So in order to extract this information, we use statistics like multiples or wedges. So just to say what the wedges are, in case you're not familiar with this, this is just an angle average of the two-dimensional correlation functions over wide bins in mu. So this is just like a really low resolution version of this map. So if you just use essentially two angular bins in the 2D correlation function, you get two correlation functions. This is what they look like. And if you use 3 bins, you get 3 correlation functions, and that we call wedges. And these are then measuring the correlation functions of pairs primarily aligned in the direction parallel, intermediate, and transverse to the line of sight. They all show the BAO feature, and the differences in the amplitude and shape of these wedges are caused by redshift space distortion. And you can do, of course, the same in Fourier space, and these are what the wedges look like on the same data set, and the color coding is the same. And for the final BOSS analysis, we use these measurements to extract cosmological information, and for that you need a model. And the model is shown here by this solid line. This is the best fitting Lambda CDM model to the combination of Planck data with BOSS. So separately for these two data sets, we got completely consistent constraints from configuration space and Fourier space. So we'll just say something about the model that we used for this analysis. So this is a one-slide summary. what the recipe that we use for the 2D power spectrum as function of k and mu can be written as a product of two functions. One, this is typical for many other recipes as well. One of these two functions is the non-virial power spectrum, that is the non-linear power spectrum that describes the effect, the Ricci space distortion effect of the coherent flow of matter towards overdensity regions. And this power spectrum is then multiplied by a factor that is usually referred to as the fingers of God factor that describes what is the effect of deviations essentially from the non-virial power spectrum. And then there are layers in the modeling of this that include, first you need a treatment of the nonlinear matter and velocity fields, then a prescription for galaxy bias, and then also to model Ricci space distortion. So we'll say a few words about these things. What we use then to describe a nonlinear matter clustering is GRPT. This is a new recipe to describe a nonlinear clustering. There is in RPT and its extensions, you always have this problem that in the RPT describes the nonlinear power spectrum as a sum of two terms. One term is just the linear matter power spectrum times a propagator, and a second term that is a mode coupling power spectrum. And the problem is that as the first term, this propagator is resummed, this breaks Galilean invariance. And GRPT is a prescription to renormalize also the mode coupling power spectrum in a way that is consistent with the propagator. And this is a comparison of the predictions from GRPT shown in orange against the matter power spectrum from the Minerva simulations that we run at MPE. This is a set of 300 dark matter embodied simulations. Alex also referred to these simulations in his talk. The resolution of these simulations is modest, maybe, but this is enough to resolve the halos of that host the Bose galaxies, and that was the goal of the project. Okay, so then you see that the predictions from GRPT actually give a very good description of what we find in the simulations up to a case larger than 0.2. This is just the matter clustering. Then you need to add galaxy bias, and this is the same recipe that Alex described in his paper, in his talk. So we have local bias parameters and non-local contributions. We saw that we can just set that gamma 2 has almost no impact on our predictions, so we can just set it using the local Lagrangian relation. But we saw that it was necessary to vary this gamma 3 minus parameter that is related to gamma 2, 1 in the notation in Alex's talk in order to retrieve unbiased cosmological constraints. So our prescription for bias has 3 free parameters. And then we need to add Ricci space distortions. The modeling for this is very similar to TNS. So I won't say much about this, but the main difference is that the shape of these fingers of God factor is not just a Gaussian, it includes an additional parameter, a virial, that represents the kurtosis of the velocity distribution, so deviations from Gaussian behavior on small scale. And we then have 4 free nuisance parameters in our model, the 3 bias parameters and a virial. So we tested this recipe using HOD samples on the Minerva simulations for low CNC mass. This is an illustration of that. These measurements here are the mean of these HOD samples from Minerva. The 3 wedges, line of sight, intermediate, and transverse, and the solid line is the best fitting model to these measurements using the recipe that I just described. On top of these tests using Minerva, we also ran other tests using the CAPSky MOX from Bose and these challenge boxes that Guido also referred to in his talk. And essentially the conclusion from all of these tests is that we can retrieve the unbiased cosmological constraints or unbiased constraints on the BAO and Ricci space parameters. So using this, then we can extract cosmological constraints from the data. And in general, the approach was always to use, we were interested in constraining deviations from the lambda CDM framework. And as we know, the CMB is very good at constraining the CMB parameters, but as long as you deviate from the standard lambda CDM parameters, the constraints from CMB data alone offer really strong degeneracies. And this is one example of that. These are constraints on the dark energy equation state parameter, assuming that it is a constant parameter as a function of omega matter that you obtain. These are constraints, 1 sigma and 2 sigma constraints from Planck, and they show this really strong degeneracy. This is something that is well known. But when you combine CMB data with BOS, then you break this degeneracy, right? And then you get constraints on tight constraints on deviations from the lambda CDM parameter. And this was the game. So you can improve this a bit if you add also supernova data, but this was the game that we were trying to play from this final analysis, trying to constrain deviations from the lambda CDM scenario. Now, since then, the focus of the community has shifted a bit. So now the discussion in the community is not that much about constraining deviations from lambda CDM, but about testing the consistency between different data sets within the lambda CDM framework. Right? So this is a different question. And when people looked at this using different data sets, they found these intriguing tensions. These are differences between the constraints that are obtained with different data sets, which individually maybe don't have enough statistical significance to be relevant or to really signal a problem, but that are intriguing, as I said before, so they deserve further attention. And one of these so-called tensions is the sigma 8 tension, and this is shown, illustrated in this plot. These are constraints from different lensing surveys on omega matter and the value of sigma 8, and this sigma 8 tension is the fact that all these data sets in general prefer lower values of sigma 8 than the ones that you would infer from Planck, again, within the lambda CDM framework. And these constraints can be expressed as a function of this quantity S8, that is just a parameter that describes this degeneracy. And yeah, so all of these data sets prefer lower values of sigma 8, of S8 than Planck. So what we wanted to do now in this paper with Tillman, Tröster, and others was to try to see if we can say something about this tension using the data from BOS. So the main reason why we always combined clustering data with the CMB is because essentially this is the information that we get from the BAO peak. And in order to obtain absolute distance measurements, you need the size of the BAO ruler. So this is the angular size and the redshift extent of the BAO scale in classic. So if you get this sun horizon scale from the CMB, you really obtain absolute distance measurements, and this is really powerful to constrain cosmological parameters. And this is why this works so well at constraining parameters like W. If you don't have this input from the CMB, then all you can measure is distance ratios, so distances relative to the size of the ruler. But even without this information from the size of the ruler, or this information is given essentially by the prior that you assume on omega baryon, you can constrain the parameters of the lambda CDM model using clustering data alone. And this is a test again, so similar to what was shown earlier in Guido's talk. This is a plot showing constraints on lambda CDM parameters using our measurements from the simulation. So these are the Minerva simulations, HOD samples matching the clustering of log C and CMAS, used separately, and then in the joint analysis in blue. And in all cases, we recover the true cosmological parameters of the simulations. Yes? I didn't hear that.
If you tune the clustering to match the observed sample, but there's a systematically observed sample that you can account for,
so these HOD samples don't match exactly the clustering measurements from BOS. These are just based on HOD feeds from BOS data. So in a sense, BOS is consistent. The data from BOS is consistent with being one realization from these data sets. If there are additional systematics, maybe additional systematics that are not taken into account in the analysis of the data, maybe this would affect the HOD fits parameters. Okay, then, well, but that shouldn't be. So if you want, this is just a test of the model, the ability of the model to recover constraints from the data. And the volume of each one of these Minerva simulations is similar to the volume of BOSS. So this is similar to what you expect using the BOSS, full BOSS array, slightly better.
So this is not the product. This is just one. Yeah. It's not the product of all the.
This is the mean. We're fitting the mean. But the error bar is the error bar of one realization. So the errors are essentially the typical errors that you expect for one realization, but as the mean is the average for this huge volume, you expect to get really the correct cosmological parameter. That's why they're centered on the true values. Yes. Otherwise, one single realization would shift, right? Sure. Okay, so then we did this using the data from BOSS, and this is what we find. The red contours are the results from BOSS. Blue is, again, Planck, assuming lambda CDM. In general, we find very good consistency between these data sets, but it is also interesting that BOSS prefers slightly lower values of sigma 8, as this is seen in this plot. When you marginalize over the other parameters, sigma 8 is a bit lower than the predictions from Planck. So I will try to make something more quantitative on the agreement between these in a minute. So just a slide on the impact of priors. As I said before, this all depends on your prior and omega variant, or your ability to constrain different parameters depends on the priors that you assume. So these are plots showing 3 different priors, what we call uninformative priors, that are anyway priors on omega variant with a width that is 5 times the 68% constraint from Planck. So this is much wider than Planck, but it's still informative in the sense that if you allow omega variant to vary freely over an infinite or a very wide prior, so it's this the blue, so the blue contours are this informative prior. This is a very wide prior on omega variant. You see that it's essentially not well constrained. If you use what we call wide priors, these are 5 times the error on omega variant from Planck. This is essentially you just recover the width of the prior. And if you use a VBN prior, of course, then this is also determined by the prior. The good thing is about that this particular panel, omega matter sigma 8, is really not sensitive to this prior. So we wanted to see what happens if you combine this with other low redshift measurements, and here this is the same plot that I showed before, but I also included here now the constraints from kids data. So these are lensing measurements that also constrain these parameters independently, also assuming lambda CDM. And yeah, separately they're not maybe statistically significant, or they're not really, well, I will say something about that in a minute, but when you combine BOSS and kids, then these constraints improve significantly. This is almost factor 2 improvement in the error. It's 45% reduction. And yes, the predicted value, the preferred value of sigma 8 is lower than this. So this than the Planck value. So this can be written in terms of this S8 parameter. This is a combination of values of S8 in the literature from this paper compared against Planck, and we can add the values that we get from BOSS only, and when we combine BOSS with kids. So this showed again this tendency to prefer lower values of sigma 8. So, but then what is the statistical significance of these differences? So I will just go to the last result. So what we use is this suspiciousness statistic. This is a Bayesian quantity that measures the degree of tension between different data sets. This is a bit difficult to interpret, but the results can be casted as in terms of sigmas tension. So if you just look at BOSS and Planck alone, you will say that BOSS and Planck are completely consistent. This tension is only 0.7 sigma, which is perfectly fine. If you look at the combination of BOSS and kids, then the degree of tension between this low redshift data and Planck is at the level of 2 sigma. So this is still not huge, but it's interesting, I would say. Okay, so then with respect to this other analysis that we heard before, and we will continue here. So the good thing about this different analysis is that although we use significantly different modeling tools, so we use a different treatment of nonlinearities and redshift space distortions, our constraints are similar. So it means that this is really the constraining power of the data, right? So these results are not sensitive to the particular choice of the model that you use, and this talks about the robustness of these results. Okay, so I'll stop here and yeah, thanks.
Comments or questions?
This is something that I was told when I was doing talk. That if you have 300 simulation, you put the product. And basically, your error bar is 1 over 2 to 300. So you can detect the system.
Yep.
You should be within the true value by 1 over 2 to 300 of what you see. So
yep.
I think that would be interesting to measure the systematic error because it doesn't look like you don't have any.
So what is relevant, of course, is the relation between the systematic error and your statistical error, right? So if you have a systematic error that is of less than 5% of your statistical uncertainty, it is irrelevant, right? So what we try to show with this kind of plots is what is the deviation that you would expect on average from the true values in comparison with the statistical uncertainty that you expect for a sample of the size of box. And as the volume of one of we designed these boxes to have roughly the same volume of balls. The idea was that just using the covariance matrix of the different boxes would give you an idea of what is the comparison of the statistical uncertainties versus systematic deviations. But you're right. So you can, yeah. What? Half a sigma systematic error, what?
You have 300 times the volume of balls. And now I just have a finally I can do it. So yeah, you have a 1 over 300 that you should be the same value by 1 over 300.
Yeah.
It doesn't look like so
but as I said before, what is relevant is not the absolute size of the systematic error, is the relation between the systematic error and your statistical error.
The difference is half a sigma. So
but the difference here is not half a sigma. So you're talking about this panel? This difference is not half a sigma. This is the low C. If you just look at the low, well, also the result is. I am not sure, but this is probably less than half a sigma.
But what is it in absolute number? Is it 105?
Maybe less than that, but yes, let's say 0.05.
That's not small, right? That's 6% from there. Right there.
For a sample that has a larger statistical uncertainty.
No, because if you divide the error by square root of 300, then you'll have something a significant deviation of the mean from the true value by 6%.
Yes.
Yeah, it's also somewhat misleading to look at marginalized posteriors though, because the maximum likelihood could be significantly closer to the truth than the marginalized means. So that's another thing to potentially look at. So the difference between the maximum likelihood of your constraints and the true cosmology in the full parameter space, not the marginalized parameter space. So this could just be a parameter degeneracy that's showing up in the marginalized.
Sure, but this is the value that we quote. So we quote the mean. What we quote in the tables is the mean value of sigma from the posterior distribution. Yeah. And the marginalized posterior distribution. Anyway, I can check this in more detail. But again, what is relevant for an analysis is the relation between the systematic error and the statistical uncertainty. Then you can ask whether this would be good enough, let's say, to be applied to a sample that would give you statistical errors that are 10 times smaller than this. And then that's a different problem.
Other questions?
Yeah, so maybe I can Sorry, on the dominant, all models give the same result. Again, I think all models are somewhat similar, and I think maybe you disagree on it, but I think ultimately there's only one model. As for the electric material, there's only one here, mass equation, there's only one. Of course, with GRPT now, if we have maybe with some critical details, which are not, of course, we're talking about this will matter at this level of the half a sigma systematic error that is there. And at some level, they're all quite similar, and it's in case in the small quantities that matters. Also, if we go to higher loops in the future. So I don't find it so.
I don't understand the
Then the fact that the all models give the same answer, I'm not sure when we look at the level of precision of this plot only shows that there is a systematic error less than 1 sigma of the data. Okay, but that's not enough.
No, from the joint analysis, the systematic error is much smaller than sigma, right? So it's not just less than 1 sigma, it's much smaller. But it's much less than half sigma in this plot. Okay. But anyway, yeah, so then the statement is that you, from both data, you can use different modeling tools and you will get constraints that are similar with similar statistical uncertainty, because the statistical uncertainty is given by the data. And that these results are robust with respect to the particular model that you use. This is my statement. And I think that
the model is very robust. We don't need to argue about the model. We have a model which is super robust.
So I'm not. I'm just saying also that it is very good that we can use different modeling tools, apply different modeling tools to the data, and extract a similar, robust, consistent cosmological constraints, because this speaks about the robustness of the results. Right?
Would you say in the electromagnetism class, I'm using two electromagnetic maximum equations for electromaterials? We use one. I mean, one is right, the other is almost right, maybe not so right. I just try to test.
Okay.
Okay. All right. Okay, let's thank our speaker again. Okay, next up, Misha will tell us about cosmological parameters from LSS data.
Hi, everyone. Thanks for having me here. This is really very nice opportunity to meet all the people working in large-scale structure, and I'm looking forward to fruitful discussions altogether. So I'm going to talk about the measurements of cosmological parameters from current and future large-scale structure data, keeping in mind the spectroscopic galaxy clustering data. So my work is based, my talk is going to be based on work in collaboration with Marko Simonovic, Matthias Zadaryaga, and Anton Chudaikin, who is now moving for his first postdoc at Perimeter, Toronto. So I'm going to present the results obtained with a new pipeline, which is designed to analyze data from spectroscopic galaxy clustering surveys. So the zeroth order idea behind this pipeline was to be able to consistently recompute the matter power spectrum and other statistics as we scan over different cosmologies. And the main feature of this pipeline, the core idea, is to use the most advanced nonlinear model for the theoretical power spectrum and other statistics, which is based on one loop perturbation theory. It includes all the developments in the field, in large-scale structure theory, all the developments which have been made in the last decade, which crucially includes the counter terms and infrared summation. And here maybe I should pause for a moment and say that since Lifshitz discovered linear cosmological fluctuations in 1946, there were numerous attempts to build a consistent nonlinear perturbation theory, and essentially these attempts, they led to the development of the effective field theory of large-scale structure, which finally gives you the only one fully consistent Taylor expansion, which relates the nonlinear density field and the powers of the linear one. And compared to previous works, I think crucially that this Taylor expansion has some higher derivative terms, which are called the counter terms, that are also characterized by some unknown coefficients, some unknown parameters, which have to be fitted. Those have to be treated as nuisance parameters in data analysis. So, and these three coefficients, they parameterize our ignorance about short-scale processes, which we will never be able to model using perturbation theory, okay? And here, as Martin is leading the session, I should say that 5 years ago, he had a beautiful paper with Matt McQueen, about one loop cosmological, well, about just cosmological perturbation theory in 1+1 dimensions, where in fact, like leaving aside these terms, you can actually resum all these deterministic terms. And then, even if you do so, you never improve upon linear theory. So you must absolutely include these corrections. And okay, 5 years ago, I just started doing my PhD. And for me, this was a clear case example showing that this is indeed the correct theory to study. Okay, then we have implemented this essential Taylor expansion with everything in the first summation counterterm, implemented this as a module to the class code. And we use the FFT-log method, which really allows us to compute the power spectrum super quickly. And as it is implemented in class, now you can take advantage of all the benefits of class, all the virtues. So it's very user-friendly. If you know how to run class, for you just pressing a button and you get all the nonlinear spectra. Then it easily scales with a number of parameters. It incorporates all possible physics and effective extensions of dark matter, dark energy, everything's already included. No hard coding, you can easily interface it with Monty Python, okay? And we're going to release the code soon, hopefully next month. So in my talk, I'm going to present 3 different applications of this pipeline. First of all, I will show some results of the analysis of high resolution body simulations. Then I will apply this to analyze the Bose data, and then I'll present a forecast for future surveys like DESI and Euclid. So once we had the pipeline, we decided to test it by participating in the blind perturbation theory challenge organized by Masahiro Takada and Takahiro Nishimichi. So all the data is available online, and if you feel good about this model, please, I encourage you to go and participate in the challenge, because this is the idea to finally pin down, to understand what is the good theory for future service, okay? So the task was the following. So if you go to this link, you will find the high resolution and body simulations. So you find the power spectrum of Bose-like MOCs with a total volume of almost 600 cubic gigaparsecs, which is 10 times bigger than Euclid or DESI will have. And the task is to measure the input cosmological parameters, which are unknown, okay? And here on the left, you see the challenge power spectra, the monopole and the quadrupole. So you see the best fit curve and you see the data points. You don't see the error bars because they are super tiny. Here you can see them in the residual plot. And you see that on the monopole, the error bars are 0.1%, and 1% is that huge. So we're able to, well, fit the spectra and recover true cosmology with 0.1% accuracy. Okay, and here I should maybe emphasize again that this accuracy is much better than the accuracy of most of the on-body simulations. With on-body simulations, it's very painful to get to 1% precision. There are very few high-resolution body simulations, and with perturbation theory, we can easily get to 0.1% and even better. Like for us, it's not a limit. So then we applied this pipeline for the real Bose data. Here you see the results for our baseline analysis. So in the baseline analysis, essentially we fixed all the parameters to some priors. So all the parameters but H0, omega matter, and sigma 8. And we're able to measure, well, essentially these 3 parameters. And for H0 and omega matter, the precision is comparable or even better than Planck. And so the final Bose data is divided into 4 data chunks that represent different galaxy populations. For each data chunk, we used 7 nuisance parameters, so 4 parameters describing nonlinear bias and 3 parameters describing nonlinear edge space distortions. And of course, the natural question that arises, okay, how would these constraints change if you include some more parameters in the fit? And this we also did. So we included NS, you can measure NS with some 5% precision. Then you can also measure omega baryons, but I think that both, like we can actually trust the measurement of omega baryons from Planck, because this measurement is model independent, because you cannot, with any new physics, no new physics can produce the same pattern of the BO-wiggles in the Planck data, okay? So we can take it from Planck, or if you don't like Planck, we can take it from BBN, but I think omega baryons we can trust. It's not vital, we can also fit omega baryon, we'll measure it with some precision, the constraint on H0 will not degrade much, okay? But in principle, you can explore the full likelihood, you can set some bounds on the neutrino mass. These bounds are not very competitive with CMB, but still. So I have some backup slides about this prior, so if you want to learn more, ask me later. here I should maybe say that the main conceptual difference with respect to previous Bose analysis, as Ariel was telling us, is that somehow previously the main idea behind Bose was to constrain dark energy and in combination with Planck. And for this goal, having this goal, it's okay to have Planck price, to put Planck price on omega baryons, omega CDM, because we know from Planck these parameters much better from Bose, okay? So in our work, essentially, the only twist is that you don't need this price, you don't need the price on RD, you can measure RD from the power spectrum itself, okay? And the shape information, in principle, is able to constrain everything. In other words, somehow, if Planck exploded, still would have very precise H0 and omega matter measurements, even without Planck. But okay, hopefully, luckily it didn't explode, and everything's good. But in principle, okay, we had some backup plan. There was a backup plan. All right, so where this information comes from? Let's take a look at the dark matter power spectrum at redshift 1000, right after recombination. So this is the seed for structure formation. So this power spectrum has many features, in fact. Of course, it has the BO wiggles, well know. Then it has some peak, it has a peak, it has some slope, which is controlled by the same parameter that also sets the position of the peak, which is K quality. Then it has a tilt, and tilt is not degenerate with the slope. Then it has a baryonic step. Somehow it's not a very famous feature, but even though it's very significant, that's why I produced this plot to show that there is a Jeans-like suppression due to omega baryons, which is 50%. And that's why you can measure omega baryons thanks to this feature. And you can measure by the RD, even in the absence of the BO wiggles, because this scale is set by RD. You can measure RD even if there were no BO wiggles. So now, what happens after redshift 1000? Very boring. The power spectrum just in lambda CDM just grows. Okay, so you rescale it vertically. If you do now parameter constraints, first of all, you use these features to constrain the shape parameters, omega baryons, omega CDM, and NS. So this you constrain in the first place and totally regardless of any late time evolution. So these constraints, in other words, those are principal components of the shape. Okay, you measure those. Then second, you constrain the freedom of essentially rescaling your power spectrum in the horizontal direction, okay? Because you have some features, in order to put them on the sky, you have to multiply by some distance. In lambda CDM, it's only H0. This is the only parameter that controls the distance. In some general setups, it is the volume average distance dV, okay? So you constrain the horizontal scalings, it gives you H0. Then you constrain the vertical scalings, in general gives you F sigma 8, because you only get to measure the velocity power spectrum, not the actual density power spectrum. But in lambda CDM, it's only sigma 8 because F has been already fixed in terms of omegas. Yeah, little omega is the physical density is rho, really, okay? So little omega CDM, little omega B, H0 already constrains F, okay? And then there is another additional effect, which is a beautiful effect for studying dark energy, but in lambda CDM is absolutely redundant. It's the Alka-Paczynski effect, which allows you to measure in a model-independent way the radial and the angular distances. Okay, in lambda CDM, so you have already measured all the parameters from these effects, so you get nothing from Alka-Paczynski, and this, by the way, was already emphasized in the original paper. But for dark energy, this very strong effect, this very good thing. Okay, so we have done this for Bose. What is going to happen in the future? This we already know, because we did a forecast for a Euclid or DAISY-like survey. And the main idea behind this forecast was to be as realistic as possible. What if you give me the data right now? What if Euclid already measured everything, you gave me the data? So we use the same pipeline, we use the same full nonlinear model, we run the whole MCMC with a bunch of nuisance parameters. I think that in total we had 50 nuisance parameters and all cosmological parameters without any priors, also without the prior on omega baryons. Then the idea was to keep totally agnostic about bias, about these biases and nuisance parameters. So we put no priors on them and marginalize over those. And by doing this, we also marginalize by other systematic effects like fiber collisions or redshift errors, because these systematic effects, they have the same K dependence as the counter terms. It's K squared or short noise. That's why when we marginalize our nuisance parameters, we also marginalize our possible systematics. And we use the same data class as we have now. So we have done all this, and we have found, okay, first of all, we have found that you will be able to measure the cosmological parameters of lambda CDM with the same precision as we have from Planck. So here, for example, in this plot, you see the posterior for little omega CDM and Hubble. Okay, this is the dashed line is the current, the actual Planck contour. The red line is the power spectrum constraints from a Euclid-like survey. Then if you add the bispectrum, then this curve narrows down. If you combine it with Planck, the most important thing is that these two contours are orthogonal to each other. When you combine, you gain by a factor of u, okay? And in this analysis, we didn't use any priors, even like on omega values, we didn't use a prior. Crucially, using this information, you will be able to constrain the neutrino masses, and you will be able to get constraints much better than we have now. Already with the power spectrum of Euclid, you will get one sigma error bar essentially of 30 milli-electron volts. If you add the bispectrum information, you will improve it by a factor of like by 30% or so. So now it goes to maybe 15 milli-electron volts. If you combine with Planck, it goes all the way to 13 milli-electron volts. In other words, you will be able to measure the sum of the neutrino masses, even the minimum one at 5 sigma, using the pipeline which is already built, which is already there. And I guess that it answers the main question of this workshop. Are we ready for the future? I guess the answer is yes, at least from the perturbation theory side. All right, still there are some improvements that can be done. So let me discuss these improvements. One very important improvement is the use of the theoretical error. In perturbation theory, we always compute things at up to a certain order, and we neglect higher orders. Here in this analysis, we did one loop perturbation theory, we neglect two loops. But still we know that the two-loop contribution is not some wild function. We have some estimate for it. We know it with some 10% precision. We cannot add this to our theoretical model. Then we can add this to the covariance, because in the covariance, it's okay to be 10% imprecise. So the idea is really, okay, this is my likelihood, this is my data vector, this is my theory vector computed at one loop. This is my two-loop contribution, which I add here, and then I marginalize over this two-loop contribution. And if I do this, I will find a new covariance, a new contribution to the covariance, this theoretical covariance, which has the following form. So its amplitude is set by your estimate for the two-loop matter power spectrum times some exponent of the difference between k-bins. Essentially, this is the off-diagonal part. So the most crucial thing about the theoretical error covariance is that it's off-diagonal. Okay, by the way, this is very simple way to estimate off-diagonal covariance for any analysis without having to run thousands of mock simulations. Well, anyway, this off-diagonal element essentially reflects the following fact that the two-loop contribution is not some wild function. If it moves one point here, it will also move the other points. So it moves the data points coherently if you add it or remove it. And this is reflected in here. And from this, for instance, it's clear that even if you blow up the error bars and go to higher k-maxes, still you'll be able to get some new information, because there are features like the BO feature, which cannot be modified by the two-loop contribution, okay? And also the equality. K-equality is very infinite scale with respect to k-nonlinear. That's why you still will be able to constrain this. So here on the right, I'm showing you the result of fitting some high resolution and body simulations. So cosmological parameters with and without the theoretical error. So let me do first the standard analysis, just increase the k-maxes. So I started some low k-max. Okay, I fit more or less everything. I'm unbiased. I keep increasing my k-max. I quickly get biased. Like my sigma 8, my amplitude gets biased. If I were to do k-max, I would say, okay, I have to stop here. I would just see, okay, these things, they fall apart. I shouldn't take this. But if I take into account the theoretical error, then I'm able essentially to go to arbitrary large k-max, and then I will take advantage of these BO wiggles of some shape information, which is still already there, which cannot be modified by the two loops. Okay, so I got, those are the results obtained with the theoretical covariance, and crucially for things like H0 or little omega CDM, the improvement is factor of u. So this is one improvement which I'd like to implement in data analysis. The second one is the treatment of fingers of God. Okay, I'll be really quick. So there was a beautiful paper by Urish and collaborators, just devoted to the theoretical modeling of ratio space power spectra. And one of the main points of this paper is that there is a way to remove or sufficiently suppress fingers of God. Okay, fingers of God are some noise produced by virialized motions of galaxies in halos. Okay, and fingers of God really, they just remove information. So here in this plot, okay, those are the monopole power spectra for different galaxy samples. And this is the quadrupole. And you see that essentially this blue curve is the quadrupole as we get it from both, okay? And the orange one is the quadrupole, say, without fingers of God, which you can do if you remove the satellites, because the fingers of God are mostly produced by satellites, okay? The centrals do not move that much with respect to dark matter halos. And you see that this fingers of God suppression is a very strong effect at K 0.25 inverse megaparsecs is an order 1 contribution. So clearly perturbativity is jeopardized, okay? But if you remove the satellites, you suppress fingers of God, you go to higher K nonlinear, then you extract more information. So I guess that one very important thing to be understood in the future is how to isolate fingers of God or remove them. Maybe one way to go is to use ratio space wedges, because then you can just throw away the mu equals 1 bin, and then you live without fingers of God. Maybe it's a better idea to do multiples. All right, so I'm done. So let me summarize my talk. So perturbation theory is very precise. It's 0.1, already now we have 0.1% precision, and it can be made even more precise. Then it's very robust. We tried many different, we ran many different tests, and we were always able to recover unbiased cosmology within the expected statistical error bars. Right now, if I apply perturbation theory to the Bose data, we can find that Bose rivals Planck in terms of precision for H0 and omega matter. And in the future, we'll be able to constrain all the cosmological parameters better, well, similar or better than Planck, and crucially to detect the neutrino mass at 5 sigma. Thank you.
Question? As a three-point guy myself, I'm very excited that my spectrum can add to the neutrino mass, but I did wonder, first of all, what different bias parameters and other things would be marginalized over in that forecast?
Okay.
Do you think that matters a lot?
Oh yeah, it matters a lot. Yeah. So in this forecast, to get this contours, essentially we used only the 3-level bispectrum. And so essentially we had only two bias parameters, but these parameters you also have in the power spectrum. That's why you gain when you add this. Of course, if we add one loop, you have more freedom. You have 11 nuisance parameters now. In this forecast paper, we did an ersatz analysis where we use the K max as if we included one loop contribution without introducing new nuisance parameters. And the upshot was the following, that without the Planck data, the improvement was very big, like factor 5 or 3 or something. But with the Planck data, the improvement was more modest, maybe some 20%. So from this forecast, I got an impression that the bispectrum is also, I mean, it helps, but its help is limited. I think so, yeah, because, okay, the bispectrum is important because it allows you to break degeneracies, but also you can break degeneracies with Planck. So at this point, the bispectrum doesn't add much. Crucially, the bispectrum doesn't change the orientation of this contour, say. You see it only like it narrows this line, but it doesn't actually shrink it. Yes? Because we had an agreement to present result at some K-max, in fact. So at point 2, we submit the results at point 2 because we decided to be a little bit conservative. But in fact, we find out that we can feed things even at higher K-maxes. But also you should understand that this volume is much bigger than Bose. If I rescale the covariance to Bose, then we're able to go to much higher K-max.
Why are you showing this 0.1%? What happens above that?
Well, above that, okay, until point 2, essentially, you're able to fit everything. So I could have shown the plot up to point 2. I'm showing you point 12 just because we agreed this is consensus result that was submitted to Masahira.
What is challenge? What is the arrangement?
For the challenge, the covariance matrix was diagonal.
Or even for this estimate, it was diagonal.
For which estimate?
The one you were showing right now?
Yeah, for the PT challenge, the covariance was given to us. It was given diagonal, but I think it doesn't on these large scales. It doesn't actually matter. I also did an analysis with the off-diagonal covariance, and then the constraints didn't change much. Yeah, this is essentially. Yeah, you mean in this or in the challenge? So in the challenge, the covariance was based. They had 10 different realizations. It was like diagonal extract from these 10 realizations. Yes. So we fitted the mean of essentially 10 realizations and then rescaled the covariance by square root of 10.
What does it mean no mean for omega b?
Oh, in this analysis, you can actually measure omega b. With Euclid, you'll be able to measure omega b with precision better. Right now, you can measure omega baryons from both data with precision 20 times worse than BBN, okay?
Yes, but then we also give you a huge error on H. If you
no, here, no prior, and still you're able to measure H. No prior, you're able, if I put this prior, then my H will be twice smaller, my H posterior.
Seems to me that if one of your comments about B1 loop, seems to me that it would be interesting. If one goes higher order, to give an order in an n-point fashion, should go to one less order in an n plus one fashion. If one does the one loop per spectrum, can do the three-level
Trust spectrum, right?
And so on and so forth, because it's the same kind of amplitude.
Exactly. Yeah.
So I think this. It'd be nice to see also.
Yeah, to add it, yeah, sure, yeah, I agree.
Yeah, just a comment. I think we should be cautious about these, expectations for high precision of measuring neutrino mass in terms of real galaxies, because if you take about simulations including massive neutrinos and build galaxies in a simplistic way as you want in the simulation, you see that these constraints become much looser. And so I think, although of course we are all going after also this, there is a lot of work to do on actually modeling the galaxy distribution on top of the theory. It's not only a matter of bias parameters, but really understanding how the galaxies that we will use will trace matter. I wish we could have that precision, but at the moment, you just compare what you expect from expecting to measure the matter power spectrum or measuring the galaxy power spectrum. And you try to constrain the figures, there's a difference of the magnitude in general. So there's a lot to learn.
But do you mean if you try to analyze this data using some emulator or something?
Well, I think this is essentially what you see at the moment if you take numerical simulations, including the neutrinos, and you say, well, what do I get if I just use the theoretical power spectrum with the bias description, etc., you get what you get. Or if I measure the power spectrum of the galaxies I created in my simulation as they have data, and I try to constrain my neutrino mass with that, you get significantly different results. You know, the yellow bars are much larger. So,
I see, but I think that yeah, I think that in theory we know how to describe it. Okay, in theory there are no this. I mean, if you do simulations, yeah, I think it's a big problem how to properly include neutrinos, for instance, in the body. There are many groups working on this, so I understand that this is a big problem.
The problem is not how. Okay, there are problems with how to put neutrinos, but the problem I think is that you are going to use galaxies. So galaxies trace the matter power spectrum in their own way. It's not a matter of the bias function is very complicated. This is what you see in practice.
Are you referring to the fact that this bias expansion at some point, like the vanilla bias expansion, is not sufficient? Yeah, the work claims like this. Yeah, I'm actually right now looking into this. Yeah, this is a legit point. Yeah, I'll be happy to discuss this. Yeah, I agree.
Sure. Yeah, what's your K max on the Boss analysis?
0.25.
So,
And are you using the standard nearest neighbor correction for the fiber collections?
In fact, we're using the full window, also the effective window function. We have done both the effective window function, but now there is absolutely zero difference. The difference is smaller than 5% on the posterior. Everything is absorbed into the contour terms.
Okay, I'm surprised that there's this little difference between using F1 analysis and using standard nearest neighbor. Because the power to measurement should be, it scales larger than, I mean, Chang would know this much, I'm just looking at his paper right here. It scales larger than k of 0.1, you get bias measurements to the power spectrum of the nearest neighbor correction. But I mean,
but if you don't include, okay, for the monopole, if you just vary the shot noise absorbs everything, right? Then for the quadrupole, the baseline analysis of both didn't have any nuisance parameters. With the EFT, we have nuisance parameter for this. We marginalize, it's totally absorbed into these parameters.
Okay, let's thank the speaker again. And the last couple for lunch, telling us about logical analysis of LSSD.
Okay. Hello, my name is Byeonghee, and I'm graduate student at UC Berkeley. And today I'll talk about the LSS analysis of the BOSS data. And I'll both talk about the perturbation theory model and also the emulation, the base modeling to constrain F sigma 8 parameters. So first, the overview. So I take the perturbation theory model developed in Rush's group and apply it to the BOSS data, showing that our model provides a competitive constraint on the growth of structure. And when we analyze the posterior of the cosmological parameters of our interest, we use a new optimization-based method called LO, which is as accurate as MCMC, but its computation cost is only a fraction of MCMC. But there are limitations of this perturbation theory approach, because it cannot accurately capture the effect of nonlinearities especially on small scales. And it's kind of unclear how sensitive the cosmological growth of structure measurements are to the small scale, the physics. So one of the most promising methods is to include this small scale information, and it's the simulation-based modeling. So the perturbation theory model I discussed in this talk also includes a calibration from simulation for key terms. And in the second part of the talk, I'll present the galaxy power spectrum emulator developed by Elena Massara, and how I use this to constrain F sigma 8 on the simulation data. And lastly, I'll briefly discuss what I plan to do with the data from the upcoming, the future, the spectroscopic survey like DESI. Okay, in the first part, I'll describe this perturbation theory model developed by Nick Hand and how it's different from others, and what pipeline I did develop for the analysis, and lastly, the RSD measurements of the BOSS data. So in the redshift space, we can decompose the contribution to the galaxy, the overdensity field, into the contributions from the C, which is the central, and S, the satellite galaxies, as shown in the first equation. So then the power spectrum of the galaxy power, this galaxy density field, can be written as the second equation. So we see the combination of the auto and the cross power spectrum. Here we wish to separate the one halo and the two halo, the terms. So the one halo means the contributions, the correlations of the galaxies in the same halo, and the two halo is is coming from the galaxies in different halos. So to do this, we further decompose the central and satellites into subsamples. Here we call it type A and type B. Here the blue dotted circle indicates the halo. So for the central, type A means the central without any satellites, and for type B, it's the central with the satellites. Similarly for satellites, type A means the satellite with no neighboring satellite, and type B is the one with the neighboring satellites. So the advantage of this is we can easily model the one halo, the contribution. So here we can see the one halo term is coming from type B central and satellites, and between type B satellites. So we can write down the equation for the two hello terms and also one hello terms, and we see where the contribution is coming from. And we write down this term as a white noise. And the finger God effect is a full like nonlinear process. So we cannot like accurately model it using the perturbation theory. So we use some damping the function. So here we use a modified Lorentzian of this form. And here the sigma v denotes the velocity dispersion. And we see, as shown in the figure, we see that we can accurately model the finger God effect over a wide scale of the wide range of scales, extending to k of 0.4. And one great thing about this model is in most other models, they assume a single velocity dispersion term for the whole sample. But here, we better account for this effect by having a separate velocity dispersion terms for our subsamples. So here's our full parameters of this perturbation theory models. And I'll briefly talk about the likelihood pipeline. And to measure the pulse spectrum, I used a Python package. It's called Embodykit. And here we use the Yamamoto estimator. And using this, we write down the multiple estimator right here. And second, we need to account for the effect from the survey geometry when we compare our theory model to the measured pulse spectrum. So to do this, we compute the window function multiples in configuration space using a pair counting algorithm implemented in Embodykit. And as you see, it's here the resulting the multiples of the boss CMS NGC samples. And on the right, the effect of the convolution is shown here. And the last piece we need is a covariance. Here, the simple one we can use is the Gaussian covariance from Grip et al. Here. And when the mean number density n bar is varying in redshifts, we can write down the per mode variance as the second equation here. And alternatively, we can also use analytical model to get the linearly diagonal and full length covariance, which is called the disconnected covariance. Here we use the model from In's paper. And compared to previous works, which only captures the size of the geometry, but ignores its shape, this has a proper treatment of the window function effect on the covariance. And I would not go into the details, but yes, you can see we compare the diagonal, the one from the Grip et al. Versus disconnected, which are from In's paper, the blue versus green, and they are about the same. So these are the constraints on F sigma A on the CMS NGC samples. And also I am also doing the more complete analysis using the full covariance, which includes off-diagonal and connected pieces, which are important on small scales. So for now, as a preliminary analysis, we get the connected pieces by running PCA on like 3x3 the blocks of the multiples. And we found like good agreement between the analytic covariance and the covariance from like 1,000 patchy mock simulations. And adding these connected pieces increases error by like 30%, but this is like quite preliminary. And so we have all the ingredients now. So we have the measurements, and we have the convolved theory pulse spectrum, the window function effect taken care of, and also the covariance. So we can write down our objective function and estimate the best fitting the model parameters using the map optimizations and using the BFGS algorithm here. And finally, we can use the MCMC to derive the likelihood distributions of the model parameters and the constraint F sigma 8 as shown in the figure here. But here in this work, instead of MCMC, we use the new posterior inference method called ELO, which gets the MCMC posterior quite accurately, but at a much lower level of computational cost. So in MCMC, we draw samples from probability distribution, but then instead of trying to deal with the intractable computation involving the posterior, we just get the samples from distribution. However, on the other hand, the VI, the variational inference, try to find the best approximations of the distribution among parameterized family. So in order to find this best approximation, we follow some optimization process. So over the family parameters. So the first thing we need to do is set up the family of the distribution. And for example, say if our target distribution is multimodal, then we can think that if you use a family of the mixture of two Gaussians instead of the family of a single Gaussian, then we can better approximate we can get the better approximation using VI. So how to get the best approximations? So we minimize this scale divergence, which is basically measuring how the one distribution is different from the others. So here's the setup, and say here the X is our data and Z is some parameters which the data depend on, and we want to get the posterior of Z given X, and we write the log posterior LP, and we come up with some model Q. So we try to fit the posterior of the Z to the model Q of Z. So as a first step, we can assume that the Gaussian ansatz of Q, and later on we can make the Q more expressive. And so we can minimize this scale divergence. And however, the minimizing this with sampling is a noisy process, but I will not go into like detailed derivation of why it is. So here we take we instead like propose a simpler and like the less noisy optimization process called LO. So we want to replace this noisy scale divergence minimization with a simpler and less noisy one. So we minimize L2 norm distance between Q and P, and we call it the LO here. So here we take the gradient expansion of the LP around the sample CK and generalize the LO to the equation below, and we stop at the two expansion term. So we use the gradient here and the Hessian term here. So like to briefly explain the advantage, like, so here we say we take we say our posterior is 1D Gaussian, and then we can write LO as a quadratic equation in the Z, the sample Z. So 3 samples should be sufficient to get the complete solution. And however, the VI is very noisy and it takes many iterations to get the right, to get to the true solutions. And here's the algorithm for the full-length Gaussian cases, but I'll skip it later. And also here, we can certainly go beyond the family of the full-length Gaussian. So here we enhance our model like using 1D bijective like transform, and we use a family of models that gives skewness and the kurtosis. And we can also use like the Gaussian mixture model. So back to the RST example. So if we use MC, then it takes about 10 to the 5 calls to converge. And we have to start from the place where the map converges, and otherwise it never converges. So now instead of we use LO, like, so we start with map, and then we switch to sampling from the QR model, and then gradually increase the number of the samples. And overall, we need only a total of 125 likelihood the evaluations. And we find that LO gets the MCMC posterior quite accurately. And as I mentioned previously, the greatest advantage of LO is computational efficiency. So LO is about like 1,000 times faster than MCMC and about 200 times faster than the BI using the same parameterizations. And now we use this posterior inference method to obtain the F sigma 8 constraint on the boss data. So first, we applying the model to the boss data, like loci and CM separately. We can see that the monopole, quadrupole, and hexadecapoles are the model quite accurately up to K of 0.4. And here is our F sigma 8 posterior. And you can see that we tightly constrain F sigma 8. And with AP parameter fixed, we get 3% constraint on CMS and 4% on low Z. And this corresponds to a total of 2.8 combined. So a few things I should mention is like the small scale information helps. So compared to the K of 0.2, like we get like about roughly 30% improvement by extending to K0.4, and also including hexadecouple F-sigma constraints improved by roughly 35%. So here's a quick summary, and I'll come back later. And in the beginning, like I already mentioned some of the limitations of our perturbation theory model and why the emulation-based model can be useful for future survey analysis. So here in the second part, I'll first go over the emulation algorithm developed by Elena Massara and how I'm using this to constrain the growth substructure. So the structure of this algorithm is shown like here. So with a given cosmology, we generate the nonlinear density field using FastPM. And then like we identify halo using friends of friends algorithm, and we populate the halos using MBodyKit and get the galaxy power spectrum. And in the following slide, I briefly show like how the sampling variance and the residual noise can be corrected and how the BAO wiggles are analytically modeled. So like there are many ways to remove the sampling variance, like without using like many like large number of realizations. But since we are out of time, I'll briefly like I'll skip the sampling variance cancellation part and then go right to the how I use a pair simulation. So basically what I'm doing is first I add the linear power correction term, and then we can use like more comprehensive the sampling variance correction method using the pair simulation, which is basically we assume like the density field is which is a Gaussian, we write it as a complex number, and we generate like two different simulations with the same amplitude and with the phases differing by pi. So we see that the better density field they have like these two better density field have opposite signs. So using this, we can estimate the power spectrum B1 and B2, which are the power spectrum in the evolved field of the two pair simulations. So and also we also fix the amplitude of the density to 1. Then the initial power spectrum of a single realizations that reproduces the sample average linear power spectrum. So we combine these two methods and they create a paired and fixed amplitude the simulations. So in this plot, we show that the performance of different sampling variance like removal method. We take the monopole, quadrupole, and hexadecapole of the redshift space galaxy power spectrum and compare the predictions from this emulator to the ground truth. The ground truth here is the ensemble average from 70 different independent simulations. And we see that the best method is the fixed plus paired simulations, whose RMS error is about like roughly 3 times lower than that of the simulation with no sampling variance correction. And similarly for quadrupole and the hexadecapole. And you see the hexadecapole is quite noisy and difficult to model. And we also do the splining. So we create, but for the time being, I'll skip the spline part and the BAO wiggle part and show how I use this emulator to get the optimizer. So basically the idea was we are using spline function to remove the residual noise. And because spline, like smooth is a function, is not suitable for the BAO wiggle. So what we do, we take out the BAO wiggle from the power spectrum and spline the ratio between the linear and the nonlinear, the multiples, monopole, quadrupole, and hexadecapole, and just find the results. And later add back the BAO wiggled with the nonlinear damping term here. And as a result, we see that the monopoles can be predicted within like 1%. So we get sub% accuracy, and quadrupole is also pretty accurate when we also get only a few % error. And hexadecapole is pretty noisy, and we have like about 20% error between this scale 0.1 and 1. And now I'm using this emulator to get the galaxy power spectrum multiple and use like different optimization algorithms to constrain cosmological parameters. So here, the objective function is data minus model, where the data is the ground truth, the ensemble average of 70 different simulations. And the model is the predictions from the emulator. And we have 7 different parameters, 5 from HOD and 2 from cosmology. And we have F sigma 8 as one of our parameters. And for the algorithm, we use the BFGS and Gauss-Newton to minimize our optimization, the objective function, which are the data minus model. So we start the optimizer at some initial cosmology and some HOD parameters, which are the red dot in the figure here. And we first need to evaluate find the different gradients. So since we do not have analytic ones, so we run 2 additional simulations, which are the orange dot in the figures. So we have to run like 3 simulations at each step. The reason why we run this 2 additional simulation is to get the numerical derivative with respect to the cosmological parameters. Here we have 2. And also we have to get the gradients of the 5 HOD parameters by running emulator at this red dot, but these are pretty fast compared to the running the full simulation. So after we get the gradient for all 7 parameters, we can move on to the next point. And after 2 to 4 steps, we say we are closer to the ground truth, and we say that doing the linear Taylor expansion is good enough. So we write down the quadratic expansion of our objective function and fit for the coefficients of this objective function. And we get the better approximation of the numerical gradients. So here's the results. So here's the method I use to do the optimization. So I'll skip it to the actual results. So when we get the numerical gradients, this is for the cosmological parameters, we also use a spline to remove the residual noise on small scales. And we can see that we only need like few simulations to reach the convergence. So here's the results. So in blue, in red, we get the constraint from monopole and quadrupole. And in blue, we add hexadecapole. And we obtain about like roughly 8% constraint on F sigma 8 on the simulation data we have assumed. And only few simulations are needed to reach convergence in this case. So this is basically preliminary the contour plot of like 7 parameter, 5 HOD here and 2 cosmology. So in summary, so in the simulator, we can reduce the sampling variance with only 1 or 2 derivative realizations. And modeling the galaxy power spectrum as a spline function and the BAO wiggles, we can have high accuracy, the predictions on monopole and quadrupole. And we only need like few simulations to get the constraint on F sigma 8. So this emulator can be pretty useful for large survey like this. So the last question is what can be done with the future survey like DESI. So I can measure the power spectrum multiples from DESI and apply this perturbation theory model or emulator to DESI and doing some cosmological analysis. And we can also get the better, like the hybrid covariance from the disconnected and the connected pieces. Thanks. Yeah, so after we find the ratio of the nonlinear and the linear, the power spectrum, we just add back the BAO wiggles with this damping term here. So we basically get the ratio between the wiggle and no wiggles and approximate the nonlinear damping term as here, and we get the theoretical prediction for this the ratio. So full fast simulation, if wiggle, non-wiggle. Yeah.
For the covariance, like like why did you use the PCA plus the Gaussian covariance for the patching mode? Like instead of the patching mode, you use the Gaussian covariance plus the PCA.
Yes.
Do you change cosmological parameters in your covariance?
Pardon?
Do you change cosmological parameters in your covariance?
What do you mean?
Why do you use analytic this covariance plus PCA? Why not just use patching modes?
Ah, I see. So like for the future purposes, yeah.
Or maybe it would reduce noise to the off diagonal.
And as you can see in the plot here. Right. So the Mach 1, I haven't plotted the Mach 1 here because of the noise in the Mach. Like they do not like mesh exactly to the disconnected plus connected ones. So we yeah. Yep.
Question. When you say you had a fixed less paired simulation, so first, what does it mean? What does it mean? And also, why is that one better than
Sorry. So what I mean by the fixed simulation is setting the amplitude of the density field to 1, and why it is better than doing the simple the pair simulation is we can assume that the initial path spectrum of like one realization is like pretty much the average of the linear path spectrum. And so that we don't have to do any like further like the correction for this. Pardon?
the paired one? The
yeah, it's not.
And also for the it's quite impressive if you need a few steps for two cosmological parameters. But how does that scale? How do you expect it to scale with more?
Oh yeah, so like H0 and all like.
Yeah, you have more.
I don't think so. Like so, as long as I can get the pre-accurate I am actually testing this forecast using like few more parameters like omega matter and the H0 and so on, and as long as I get pre-accurate numerical gradients, as long as it's not very noisy, then the number of steps do not increase drastically.
Okay, Zach.
This work is on simulations as well, right? Just going back to the Jan paper, that big model you're using, he, I think, found like 7.2% chance on that sigma 8, unless I'm misreading that. So it seems consistent with what you're doing, but why didn't you do much better if you've added all these additional modeling details, or is it more robust? And what's the
I mean, like, I think the 7% you're referring is with the AP, the free, and with the AP fixed, then the constraint gets much tighter in this case.
I think the 7% is fixed. Depends on the camera. But like, what is the additional stuff beyond the hand model here?
Not really. So we have like things I did differently than the what's shown in this paper is getting like better with the calibration term for this from the simulation. That's one thing for like velocity dispersion terms, and I use a tighter like the priors on them. That's one thing, and I also use like the different optimization algorithm, but I don't think they'll make any much difference on this.
The optimization algorithm is not much faster.
It is faster, but I don't think it's gonna affect the constraints too much.
There's no further questions. Thank all the speakers again. We can break them up.